right. And yeah, I'll go ahead and share my screen. And what we're going to do, we're going to talk about first optimizations. Or finish off optimizations, which shouldn't take too long. I think we were kind of at the end of it, but we'll do a very, very quick review just to kind of remember what we talked about. Okay, here we go. And then get my screen back. All right, so we talked about, a couple study groups ago, we talked about overfitting, making sure things don't overfit. And then we started talking about optimizations yesterday. And so we're going to continue that on. Just a quick thing, remember optimizations, basically they kind of do two things. One, basically, it just makes the model, we're able to converge to our global minimum faster, optimized, right? But also it can actually make the model perform better. So we're actually able to find those global minimums, meaning that, your accuracy will go up, your score will go, I'm sorry, your error will go lower, but we'll also get there faster. That's the idea of optimization, right? For, what's it called? Our neural networks and stuff like that. And so I pointed to a couple of resources, Keras optimizers. We've been using Keras, right, and the curriculum as well. Also, things like TensorFlow, which is a package for especially for deep learning. Basically, you can import Keras directly, so that's really nice to have. I put out this optimization blog post here. I will also recommend, I've said this a few times now, the hands-on machine learning with scikit-learn and TensorFlow. I always forget. I have it in this guy. It's such a long time, I can never remember it. Hands-on machine learning with scikit-learn and TensorFlow, then a whole bunch of type long thing. So again, I'm going to recommend that. They have a great chapter. I think it's right here. They have a great chapter on optimizations. I don't know if I mentioned this last time about it, so I'm kind of bringing it up now. So you can see all the different stuff we've already learned before. And optimizations. I know you're here somewhere. Nope. Okay. Well, there it is. Faster optimizers, momentum optimizers. Okay. Yeah. So these are like a lot of stuff. Like I would say that goes in a lot more detail and a lot more practicality of what you would do in practice and in production than like what the curriculum necessarily showing. So it's a good thing. I think that he does a great job of talking with these optimizers and really end up explaining like what these differences are. So yeah. So a few resources, right? Vanishing gradient problem, remember we talked about this. Basically, it's just that the gradient tends to disappear as we do our back propagation, which means we're not able to like get to the answer, right? Basically, we have our guiding compass, gradient descent, kind of start getting weaker and weaker essentially because this gradient is just too small. And we get slow training, we can't find the local minimum. We talk about like finding kind of like that, like we're kind of stuck in this low point, but not the lowest point. We said one of the solutions was activation functions. Remember that we should basically focus on ReLU. ReLU generally is a good all-around like default. There's a lot of optimization that's done, or that's the package is optimized for ReLU, so you can actually run it faster than what you normally would if it wasn't optimized. But there's other things like leaky ReLU and some other ones like talk about like exponential ReLU, or not exponential ReLU, exponential leaky. Actually, no, it's called ELU, like ReLU but E. Those are ones that will technically, like these guys will take longer to actually converge, but they might get better performance. However, because ReLU's pretty optimized, in general, you can probably just use ReLU and not think too much about it because you'll be able to do more iterations faster. So within the same amount of time, you probably would be able to get the similar performance. Okay, cool. We talked about random starts. So basically there's kind of like grid search, but like with randomly searching, basically just starting in different spots so we can find those global minimum compared to like finding the local minimum like in this graph. I think this is where we talked about last was momentum. And momentum basically was a new way to update our weights so that we basically can kind of power over these little hills and stuff. And then I mentioned also a little modification to momentum, which was Nesterov, I think, I'm not sure if I'm actually pronouncing that right, Nesterov accelerated gradient gradient. And this basically just does the same thing as updating momentum, but it just kind of looks ahead. So basically it's trying to get you to the momentum quicker. So this kind of avoids things that are like oscillations. So instead of like having your, kind of imagine like a bowling ball rolling down a hill and then kind of coming back, this Nesterov the way you update. Basically, it avoids a lot of that, so you tend to kind of like approach the end and not oscillate very much. So you get there faster and it doesn't oscillate. So pretty much if you're using momentum, you probably want to use Nesterov. There are some cases where it doesn't make sense. I'll leave you to like look at other resources like Hands-On Machine Learning. I think they have a good discussion about like, you know, some disadvantages of like these different optimizers. But in general, you would say momentum and Nesterov are pretty like standard thing you would do. Remember that real quick when just starting this clear out. This beta factor right here. So beta is going to be another hyperparameter. However, in general, you don't have to really change too much. Usually just setting it to 0.9 does decently. So you don't have to worry about like saying, oh, do I need to 0.8, 0.9, you know, 0.99 or whatever. In general, you can just set it to 0.9. It's perfectly fine. Okay, cool. All right, sound good? All sound good, good review? Everyone remembers that now. Cool, awesome. So now we started talking about actual optimizers. I mentioned normalization, batch normalization. Know that basically is just an extra step between the layers. And then I think where we left off then finally was stochastic gradient descent. So stochastic gradient descent, we talked about saying basically instead of taking the whole data set, feeding it forward, doing back, seeing how well it does, propagating that error backwards, back propagation, and then, you know, doing that process again. The thing is that feeding the data through, that's not the slow part. The slow part is that you're feeding back all of the errors, not from just one data point, but let's say you have 1 million data points. You have to basically adjust all of the weights, all the little dials on the neural network when you do back propagation. So one thing we can do to kind of speed up along this process is stochastic gradient descent. And stochastic just meaning random. Basically, we're taking small bits we're randomly sampling from the larger data set. So instead of having 1 million data points, maybe you only take, you know, 1,000 at a time and you push it through, feed it forward, see how it does, and back propagate that. And it means that you're not gonna actually get the most optimal like step forward with your back propagation. However, you'll get in the general direction. And the idea is that if you randomly sample, we would randomly kind of get to better and better. So we can take bigger steps, kind of like usually compared to like a drunk person like walking down, you know, like the steps or something like that. It's like they're not going the best direction, but they're going close enough. Okay, cool. All right, and so that is stochastic gradient descent, and I think we're all caught up then with what we talked about last time. So now we're going to talk about autograd and Rmsprop. So I think this is mentioned in the curriculum at least partially, and so basically a quick thing to kind of know is that autograd tends not to actually be used. It just tends to stop too early in complex problems. Basically, this optimization just doesn't work very well complex. So in general, autograd is avoided. However, it follows with like what Rmsprop is doing. So it's kind of used to understand like where it's coming from. So basically the problem with like gradient descent is that we might take too many big jumps like on a steep section. And that means we skip over something or we're not careful enough. So autograd and then therefore Rmsprop kind of have the same idea. Basically allows us to be really careful, or I say more careful when it's a steeper descent, a gradient. So basically autograd, what it does, it accumulates the average gradients from all iterations. So basically it says, okay, like in the past, we've been taking a step down, 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 and it averages those gradients and uses that as its how big of a step you take down. So what's going to happen is that it'll tend to be a little more careful versus like if all of a sudden there's a sudden drop, it's not just going to do a sudden drop. It's going to kind of take a more conservative step down based on what past iterations. The problem with this, like you can probably say, like I said, or probably realize with the too early and complex problems, is that you can end up having something where you're taking very, very small steps over time, especially as you're kind of getting to a point where you're getting over to something like this, like if you're kind of going like this, like very steep, and then all of a sudden you go like this and down. The problem is that most of your iterations are going to be down like this. And so by the time it gets to this point right here, which maybe the gradient is very small, the average is going to be pretty large, and you might actually skip over. Let's say this is like the minimum. You might actually end up skipping over this part because their average was so large. So it's hard to actually find these parts, and it'll stop before it gets to this part. Rmsprop kind of has the same idea, except instead of keeping all the iterations and averaging over them completely, what it does instead is that it'll basically decay the older iterations. So basically these older iterations are kind of like forgotten over time. So the idea is like you care most about like where you were most recently, and then you kind of add in like but we had stuff in the past, and you kind of keep that in mind. So Rmsprop is generally used over Adagrad. Like Adagrad pretty much is not used at all. And so I think I had a little visualization kind of built around here just to kind of show you a little bit what that looks like on the contours. So this isn't like code you need to worry about for the actual, optimizer, but the way this would kind of look like is Adagrad would kind of like tend to move pretty, kind of like go forward like this, and Rmsprop might take a little bit more time. Like it'll take more careful steps versus like having these very big steps going forward kind of deal. So it's kind of averaging it over more and more. Okay. So, and that's something you can just optimize, basically just declare directly from here using Keras. So you can use Rmsprop. And then you keep the learning right here. Note that row is technically another hyperparameter. If you want, you can look more into like Rmsprop and what exactly that value is. I'm kind of avoiding a little bit of, what's it called? Some of the extra math. But no, basically the root means, like you see RMS, root means square. That's the kind of idea here. But that row basically is hyperparameter. But in general, 0.9 is a good value. It's not another hyperparameter you really have to tune too much by itself. Okay. Oh, I think Andrew.
And that represents the decay rate, does it? So
yeah, it basically represents how much you decayed over time. Yeah. So, okay, cool. Sound good? So another optimizer that would be in general pretty good. I will say that in general, we'll talk about Atom next. Usually you'll see Atom optimizer used a lot more frequently than Rmsprop, but sometimes Atom, we'll see in a second, doesn't do as well. So you might use Rmsprop instead of Atom, depending on the problem. And the way you know this problem, basically you don't know until like you try it out, or there are some kind of like general rules, and the best thing to do, to be quite honest, is just seeing what other people have done and what other researchers have kind of like looked at and saw what's done well. That's where I'll point again to the hands-on machine learning book, the second edition especially. They have some, like, I think they have some general general rules about like what optimizers to use based on the current research. So I think it does a pretty good job of summarizing that. So again, really great, like practical like book to use. But know that in general, Atom usually is kind of a default. For example, if you go to Kaggle, you'll probably see Atom used a lot for neural networks. Okay, cool. So Atom, which is adaptive moment estimation, which I had to look that up because I don't remember what it is. Most people just call it Atom. Optimization and other variants. So just know basically the idea here is that it's combining Rmsprop and momentum together. So you can already see like, hey, momentum's really good. Rmsprop does pretty well. Combine them together. And essentially that's what this beta 1 and beta 2 is. This beta 1 and beta 2 basically are representing its momentum and kind of equivalent to this row. Okay, so in general, these are pretty decent values. You can see 0.9, 0.999. Those don't really need to be changed too much. You can try to play around with them if you like, but they're not something that's typically trying to search. It's not something to do a grid search over. Okay. So note that there's also an Atom, right? So these are other variants, and there's a lot of other variants that you can look at that are based on Atom. But an Atom is basically using Nesterov. So you can basically use Atom with Nesterov, and you can see here an Atom right here. And basically it's the same thing, except now it's trying to avoid that, what's it called, oscillation, essentially, with the momentum. Okay. Note that, like I said, sometimes Atom just isn't good for a good data set. That's when you can start using other alternatives. A good go-to is like using momentum with Nesterov. You could try using Rmsprop. Sometimes that's gone back. I think in general, Autograd is like pretty much not used at all anymore. It just doesn't do well for complex data sets. Rmsprop you might still see, every now and again, but in general you'll see Atom or just using basically momentum. And if you remember back when we did momentum, what that looked like, the code, here it is. Like you tend to see this with the stochastic gradient descent. Okay, cool. Any overall questions on these? All right, so Yeah, awesome. And if you're curious, definitely go through Keris's optimizers research, right? These things are constantly like, we have an optimizer and then a researcher finds an even better way to optimize it or a method to go through. In general, I will say is that there's a trade-off between complexity of like how do you implement this part and the what's it called, how well it performs. Just kind of like ReLU and leaky ReLU is that if it's really simple for the computer to compute, but it doesn't do the best job, it might still be worth it just because it can do it faster and can compute that faster. Same thing with optimizers. Depending on the data problem, sometimes optimizers will just do better on certain problems. Okay, cool. All right. So again, another thing you can add in there. So last one is learning rate decay, which I believe, I don't know if anyone's gone through section, was it 47 then, for the gotten learning rate. I can't remember if the curriculum actually mentions this. It might, but maybe not. I will tell you right now, there's a whole bunch of things that you can do with learning rate decay. And basically the idea here is that when we have like I'm gonna kind of close this guy off because I might draw on this again, is that the idea is that when we're kind of like really high up, like steep, we kind of want to get there faster, right? To the, like, you imagine this is the minimum right here. You guys have seen topographical maps before? You guys know what I'm talking about here? Like this right here is the lowest point, and then this is kind of high. So you can imagine this like a valley that's kind of going inward, right? Like if I kind of like pulled that part down. So this is really steep, this is less steep right here. Or I should say, no, wait, yeah. Anyway, if we're going downward into this part, if we're going down this way and we took really, really small steps, it's gonna take forever to get to right here. So we want to take these big steps to get here. So that's good, so we move fast, but if we move too fast, we might skip over this minimum. And like you might, for example, if I'm kind of like going down, let's say from this right side over here, and I start going down, I go down this direction, take these big steps, and then this direction right here. If I take too big of steps, what I might end up doing is basically skip over it too much, and basically I'll never find like the exact, let's say the exact local minimum is right here. Okay, so that's one problem with like high learning rates, okay, high alphas, okay. The opposite of this is if we have small learning rates. So when we're close to here, it's really nice because then we can like make sure we get the very precise, and we're not gonna skip over any like, global minimum and stuff like that. However, if you're all the way over here and you're taking small little steps, this is when your model just takes forever, and it's like taking forever to get all the way down here. So, and sometimes too, depending on how you implement this, it might never get here. It might not find it to be steep enough for it to get to that point. So you can see there's a disadvantage between high learning rate and also disadvantages with low learning rates, okay? So then you say, okay, which one should we use? And that's just like, well, there's not really a clear one which one you should use, right? Other than like the situation. So anyone got an idea what the solution is? I can't just use high learning rate for everything. I can't use low learning rate for everything. We do both of them. So the idea is basically we have a really high learning rate when it's steep and that we want to get to that answer quickly. And then once we get closer to that answer, we're like, okay, let's take smaller little steps. So this is kind of like we're getting closer and closer. So it's nice is that if we have a large gradient, which is steeper, right, we use a large alpha. And if we have a small gradient, we use a small alpha. Pretty straightforward, right? You're like, oh, well, duh, right? So it's kind of a useful kind of step. And what's nice is that basically you can implement this by saying, well, we should get closer and closer to the answer as we do more and more and more iterations, right? More and more epochs. So the more epochs we have, the smaller the alpha should be, right? Because essentially we should be getting closer and closer, should be getting a smaller and smaller gradient, right? You wouldn't expect the gradient to get larger because you have already done most of that hard work. So this is where we basically use decay right here. So this is the learning rate decay. So this is a little factor here that you can adjust and say how much you should decay alpha. And in this case, I put like, 0.0001. This can vary, just like the learning rate. You don't know exactly what the value is, but in general, you might go between this number and like maybe like even this number. That might be the highest you'd actually go for decaying. Okay. I will note that there are other ways you can do like learning rate, like in general, this is learning rate decay, but there's other ways to implement this, which is called learning rate scheduling. And the idea there is you schedule when the learning rate should be changed. And there's a whole bunch of different ways you can change about that, but I won't go into detail. In general, this will probably do pretty well for most jobs. And sometimes as you try to get better and better, you might adjust these parameters. And you can already see, like, I think in general, you can see a little bit, like, all these different optimizations you can do and all these different, like, ways you can test it. This is where, getting the best model is not going to take a day. It's going to take some time if you wanted to really optimize this thing. But the important part is to know what kind of level you need for your business stakeholders. So whatever business you're talking to, or like working with, is what is the goal for this team? What is it that they want from this model? And using the appropriate tactic to basically get within a reasonable time with resources. If you want something, like I like to say, it's like, this is even going beyond neural networks, is like, if you want something that you just want a really quick thing that you can do within like the hour kind of deal, and you just want to see a basic, like not basic, but like a decent prediction, random forest is a pretty good option, in my opinion. Is that it does a pretty decent job. It doesn't overfit too frequently, but also does, what's it called? Can still get a lot of these complex patterns, and you can get feature importance. However, if you're working on something for months and months, it might be something worth where you're taking this iterative design of like, adjusting things as needed. Okay. Cool. Any overall questions on this optimizers section?
Does this have any problem with local minimums? Like if you slow down the learning rate, can you get stuck in a...
That's right, yeah. Oh yeah, definitely. So that's why it depends on the problem. So if the learning rate decays too quickly, so let's say, for example, I'm just kind of quickly draw. If the learning rate decays too quickly and you have a steep part right here, and then you kind of go into small little part and then go down like this, right? I didn't make that minimum very small, but that's okay. And I have my, let's say, I'm kind of walking down here. If my learning rate is too big, so it's decaying way too quickly, maybe this is going to get so small that I'm never going to really quite get there, right? Like basically my learning rate just gets too small. Opposite can happen, where if my learning rate decays too big still, I'll take these big steps over here. Maybe the next one is going to be smaller, but it's not small enough, and maybe I'm just trying to do this. You might skip over this minimum too. So that's where the learning rate alpha and decaying, saying how much this alpha change to. So like going from like a new value, so like say new value, let's say some function. So that could be learning rate or learning rate decay or some kind of scheduling, whatever changes as alpha. This is very like having the right alpha, whether that's just a plain alpha or learning rate decay or something else. Your what's it called? Your performance is going to be highly dependent on this alpha. And so there's no like right answer of exactly what to do. And that's why you're going to have to kind of see exactly. Depending on the data, some data, they can have small little local minimums spread throughout the cost function. In that case, you might want to make sure that you avoid those local minimums and stuff like this. But you won't really know that until you look at the data or really just try out the algorithm itself. Okay. And if it makes you feel better too, in general, it's pretty agreed upon is that even a really well-seasoned machine learning engineer, or data scientists who are designing these algorithms, like machine learning algorithms, there's not like someone who's like, oh, I have a lot of experience, I know exactly what machine learning algorithm to use for this kind of situation. It's a lot of trial and error and stuff like this. But that's part of the science too. Is you try something and then say, okay, what did it do? How can I adjust this to move in the right direction, or in what seems to be like in a better direction? There's still kind of like uncertainty in the same sense that if you're blindfolded, you might not know exactly what's in front of you, but you can get a better idea as you kind of bump into things. Okay, cool. Good question though. Any other questions you guys have? No? Okay, I'll go ahead and stop the recording here.